Okay, Gen Chem kids, we are going to be talking about putting molecular geometry or shape onto some of the molecules that we have been drawing the last couple days using Lewis structures. Now, in order to do this, you're going to want the molecule geometry chart that is on the next page handy. We're going to be scrolling back and forth to it, okay? So here we go. In order to determine the shape of each molecule, it's important to look at the electrons. So we're going to need to look at all the electron pairs around that center atom. That's why I've had you looking at the center atom for the last little bit. We call these areas of electron density. Okay, electron pairs, now they don't just need to be pairs. Remember, a double or a triple bond can count as one area because there's all the electrons all smushed together into one spot. So electron areas or regions of electron density like to be as far apart from each other as possible. Okay, they like to be as far apart of each other. I want you to think of electrons as negative because they are. What happens when you put two negative ends of a magnet together? They repel. So just like electrons, negatives next to negatives, they're going to repel. So they want to be as far apart away from each other. So to do that, geometry speaking, let's scroll down to this chart on the next page. So these are the shapes that we will get, and we're really only going to pay attention to these first three areas. Okay, so let's look at this first one. If I have two areas of electron density, the farthest I can get them away from each other is down the opposite side of each other. So to do that, that means my electron shape is going to be linear. Okay, so let's go back up to that in our notes. Okay, so here we go in our notes. For instance, two regions will be 180 degrees from each other. In other words, they will be linear. Okay. If I have three regions around that electron, around that center atom, let's look at three regions. So if I have three regions, I'm going to have trigonal planar. It's like an equilateral triangle. So if I go from point to point to point, I have a nice flat equilateral triangle that is all in one little plane. Okay? So it is called trigonal planar because it's a triangle and it's in one plane. That's where we get the name. It's all in one plane. So your geometry comes back to haunt you here. Okay, so three regions will be about 120 degrees from each other, and we call that a trigonal planar geometry. If I have four regions of electron density around that center atom, let's look at this. If I have four regions around that center atom, I have a tetrahedral. So if you look at that in terms of three dimensions, any of you guys who play role-playing games and you have a four-sided die, I want you to think of it as that shape. I'm going to essentially have a four-sided die shape going on there. And that's a tetrahedron, so we call it a tetrahedral shape. Okay, so four regions are about 109.5 degrees from each other, and that is a tetrahedral shape. You will need to look at this chart very often to see what's going on, okay? So Lewis structures will often not show these angles because we're drawing them on a flat sheet of paper. So you have to get in your mind how to get it to transform from that two-dimensional flat sheet of paper that we're drawing on to that three-dimensional shape. Now, there is a really good PhET. If you go onto the PhET simulations in chemistry, called molecular shape. If you have time, go and play with that. That's a really good way to learn your shapes and your geometries, okay? So these are all Lewis structures that we've drawn before. So we're basically going to be repeating the Lewis structures that we did before. So we're going to practice a few, okay? Yep, we did these on the previous pages. So phosphorus trihydride. So phosphorus has 5 valence electrons and hydrogen has 1. And I've got 3 of them. So that means altogether I've got 8. Now I'm going to put phosphorus in the middle. Now, if you want to know where I'm coming up with these numbers, you by all means can go back to the previous YouTube videos that I posted to show you where I'm coming up with these valence electrons. So here is my Lewis structure. I have 4 areas of electron density. Let's highlight them really quick. I have 1, 2, 3, 4 areas of electron density around that center atom. But notice that 3 of them are bonds and 1 of them is a lone pair. So I have 4 areas. 3 are bonds and 1 is a lone pair. So let's look at how we are going to use this chart to determine the geometry. So if I scroll down to this chart, I indeed have a tetrahedral shape, which will give me an electron geometry of tetrahedral. But my molecular, notice on the molecular, I have to pay attention to how many lone pairs I have. I said I had 1 lone pair. So if I have 1 lone pair, I am going to have a trigonal pyramidal. Notice this pair of electrons here takes up space. But when I draw just the molecule where the atoms are, it's going to be a pyramid with a triangular base, and it's not flat. It's kind of up in the air like a little pyramid. So that's a trigonal pyramidal shape. So here we go. So our electron geometry here is going to be tetrahedral, but our molecular geometry is going to be trigonal pyramidal. Okay? Okay, carbon tetrachloride. I'm just going to draw the Lewis structure right here. I'm not even going to count out the electrons. If you want to see how I did it, once again, look at my previous videos. So here's our Lewis structure here. I have 4 areas of electrons around that central carbon, and they're all bonding. So if I go down to my chart, I've got my 4 areas. So my electron geometry is tetrahedral, and because I have no lone pairs, my molecular geometry is also going to be tetrahedral. There's no lone pairs, right? So back up here, when I look at my geometry, my electronic geometry is tetrahedral. And my molecular is also tetrahedral because I have all 4 pairs being bonded. All right, hydrogen fluoride. This is my Lewis structure. Now, I don't have a central atom. And because I don't have a central atom, the only thing I can do between 2 points is a line. So I'm going to call this linear. Okay? So if you just have 2 atoms, just call it linear, and you'll be good. All right? And there's no real bond angle because to have an angle, I have to have 3 points, right? Right? By geometry definition, I only have 2 points, so whatever. All right, hydrogen sulfide. I have sulfur in the middle, and I have the 2 hydrogens, and then I have a lone pair on top and a lone pair on bottom. Now, this is one that gets kind of tricky. On paper, it looks like it would be linear, but let's check our chart. Okay, so if I check that chart, I have 2 areas that are lone pairs and I have 2 areas that are bonding, which means I do have a tetrahedral electron shape. I have 2 lone pair areas, so that means I have a bent geometry. My molecule will be bent, and so it will actually be like this. Okay, so my electron geometry is tetrahedral. My electron geometry is tetrahedral, but my molecular, because of those 2 lone pairs, is bent. Okay, so this is where paper and pencil don't really do us any favors three-dimensionally. Okay, so it's really important that you get the mental picture of what's on the paper out of your head because it's not necessarily true. So my electron geometry here is tetrahedral. And my molecular geometry is bent. Okay? All right, let's go on to the next. Okay? Now, have you noticed that on each of these, we are determining the number of regions around that center atom, and then we decide how many are bonding regions and how many are lone pair regions? Okay? So, we're going to do some more here, some more practice. So silicon tetrafluoride, I'm just going to draw the Lewis structure here. Okay, now let's look at that center atom of silicon. I got 4 areas and they're all bonding. So if I have 4 areas and they're all bonding, I have a tetrahedral shape for my electron geometry and also a tetrahedral shape for my molecular geometry because I have no lone pairs. Okay, so let's put that in here. So my electronic geometry is tetrahedral, and my molecular geometry is also tetrahedral. Okay, fluorine. Fluorine, this is our Lewis structure. Now, I only have 2 atoms, so I have no center atom. So the only thing I can do here is linear. No center atom to even worry about here. Okay, nitrogen trifluoride. Here's our Lewis structure. All right. Lewis structure. Let's look at that center atom. I've got 1, 2, 3, 4 areas of electron density. 3 are bonding, 1 lone pair. So let's check it out. So 4 areas, once again, 4 areas. I have 1 lone pair, so that gives me a trigonal pyramidal shape. Okay? So tetrahedral geometry for my electron geometry and trigonal pyramidal for my molecular. So my electron geometry, I try and draw too quickly. Doesn't have time to switch. Okay, electron geometry is tetrahedral. And my molecular geometry is trigonal pyramidal. All right, carbon hydrogen trichloride. Here we go. I've got carbon, hydrogen, and 3 chlorines. All right, let's look at that center atom of carbon. How many areas do I have? I've got 1, 2, 3, 4, and they are all bonding. Haven't we seen that a couple times? We have. So if I have 4 areas and they're all bonding, do you guys remember what it is? Let's scroll down. 4 areas, all bonding. I will have a tetrahedral electron geometry and a tetrahedral molecular geometry. So my electron geometry is tetrahedral, and my molecular geometry is also tetrahedral. All right. If you think you can do this, do a couple on your own and then pause and check. Do these next 3 or 4. Let's do this row. Okay, you guys ready to check? Okay, oxygen. This is our Lewis structure for oxygen. Now, I only have 2 elements here, or 2 atoms, so I can't have an angle, and the only thing I can do is linear. Okay, carbon dioxide. Here we go. All right, there's our Lewis structure. How many areas around that center atom do I have? Did you guess 2? Remember, double bonds and triple bonds just count as 1 area. So indeed, I only have 2 areas of electron density around that atom. So let's look at that chart down below. If I look at this chart where I have 2 areas, I am going to have a linear molecular geometry and a linear electron geometry. So carbon monoxide or carbon dioxide has an electron geometry that is linear, and it has a molecular geometry that is also linear. Okay, carbon monoxide. How'd you do here? Did you put a triple bond in here? Now, I only have 2 atoms, so the only thing I can do here is make it a line. And I have no bond angle because I don't have 3 points. I only have 2 points. Okay, cyanic acid. How did you do on the Lewis structure there? Now remember, how many areas of electron density do I have around that center carbon? Remember, triple bonds, double bonds, and single bonds are all considered 1 area of electron density. So when I look at this, I just have two areas of electron density. So if I go down to my chart here, two areas of electron density gives me a linear electron pair geometry and also a linear molecular geometry. So my electron pair geometry and my molecular geometry they are both linear. Okay, so wow, that sure took a long time to switch. Electron is linear and the molecular is linear. Okay, all right, you ready to try some more on your own? Why don't you try the next row and call back in just a minute. Okay, SO2. Let's see. We have this geometry going on. Okay, so we've got a double bond on one side, and it really doesn't matter what side you put it on. We've got a single bond on the other side to the oxygen, and we've also got a lone pair on that sulfur. So when we look at our areas of electron density, we have one, two, three. Now, two of those areas are bonding areas, and one of those areas is a lone pair. So let's look at our chart and see what that gives us. Okay, I've got three areas, so my electron geometry will be trigonal planar. But because I've got a lone pair, one lone pair, I will have a molecular geometry of bent. Okay, so I will have trigonal planar for my electron geometry, and I will have bent for my molecular geometry. Why is this freezing up? Okay, so let's change colors here. So for my electron geometry, I will have a trigonal planar. For my molecular geometry, I will have bent. Okay, sulfur trioxide. Okay, sulfur trioxide gives me this geometry right here, or this Lewis structure. Okay, so how many areas of electron density do I have around that center atom? I have 1, 2, 3, and they are all bonding. So let's look at my chart. Okay, I have 3 areas, and they are all bonding. So my molecular and electron geometry are both going to be trigonal planar. Okay, how'd you do on that one? Okay, my electron, oh wow, that still was so delayed. Electron geometry is trigonal, planar, and my molecular geometry is trigonal, planar. All right, nitrogen. How'd you do on this? This is our Lewis structure. I've only got 2 elements or 2 atoms, so the only thing I can do here is linear. And because I don't have 3 points, I don't really have a bond angle or a bond shape other than the linear. And then oxygen. O3 is not actually oxygen, it's ozone. So when I look at ozone, this is what I get. So I will have a single bond to one of the oxygens, and I will have a double bond to the other. It really doesn't matter which side you put it on. And then I will also have a lone pair on the center oxygen. So that being said, that gives me 1, 2, 3 areas of electron density around that center atom, 2 of which are bonding, 1 is a lone pair. So if I look at my chart here, if I have 3 areas, I have a trigonal planar electron pair geometry. If I have 1 lone pair, I have a bent geometry for my molecular geometry. So my electron geometry will be trigonal planar, and my molecular geometry will be bent. So let's draw this in. So my electron geometry why does it take so long to switch pens? My electron geometry is going to be trigonal planar, and my molecular geometry is going to be bent. Okay, so hopefully this gives you a really good idea of how to determine the shape looking at the areas of electron density around a center atom, and then using the number of areas and which ones are bonding and which ones are lone pairs, and the chart that we have on the next page to determine the shape of both the electrons around that center atom and the molecule. Hope you have a good time with this. See you later. Bye.